We're not going to talk very much about this crystal, zircon. Everyone loves it. Pete's given it its few moments of fame. What we're going to do is we're going to ramp it up a little bit, and we're going to look at slightly more challenging minerals to date and perform geochronology on. And we're going to look at some of the basics, and you're going to see me repeat some of the stuff that Pete has talked about, but I'm gonna take it from a little bit more of a tool perspective rather than the 101 equation style. So Pete's done me a real favor by covering the maths. So we're going to look at apatite, and we're also going to look at titanite. So these are two useful minerals, but they have drawbacks. Their drawbacks are the common lead, and how we deal with common lead is going to be a subject of this kind of talk. So you can see I've kind of modified the title a little bit. We're also going to touch on the idea of thermochronology as well. So that's rather than using the isotopic information to give us an age that a mineral has grown, it's the idea that we can use the isotopic information and with some assumptions about the fusion parameters to say something about the time temperature pathway of that crystal, and maybe say something about the lower temperature processes occurring within that geological unit. So just for a little bit of context, you can see publication year here. This is the number of papers published, and hey, no surprise, uranium lead wins on that. It's got some unique powers within this isotopic system, and Pete talked about that. You know, we've got multiple isotopic clocks that give us this ability to check for concordance or open system behavior. If there's open system behavior, it doesn't necessarily mean that we walk away and put that data in the bin. It just tells us about another geological process. These other systems don't really have that advantage, but they can tell us about other things. So in terms of what uranium lead has been performed on in terms of the crystals, zircon is obviously the most common for the factors that Pete talked about. You know, it's this refractory mineral. We find it widely within crustal rocks, and it's very robust, and most importantly, it doesn't incorporate much common lead when it grows. So that means our time signal is quite well retained within zircon. Badleite is quite commonly used as well, and that brings us into the ability to date more mafic rock types. But you can see recently this idea of using titanite is beginning to show more interest, and I would say apatite is also showing more interest. Okay, so there we go. So quick kind of refresher on the whole idea of common lead. Basically, we can use our 204 as a track to see how much lead is not produced from radioactive decay. So our 206, you can see our 206 is coming from our 238, our 235 uranium is producing our 207, and our 208 is coming from our thorium. But having an ability to measure this 204 is kind of handy, because it allows us to then, using a model, predict how much of these other isotopes of lead we need to subtract. So that's the situation that we want. We don't want any common lead. We want our parent uranium to change to lead. Happy days, we get a clock. We have that, and we have some common lead there. We need to know how to subtract that. Otherwise, our clock is going to be a little bit bust. Very simply, oh yeah. And I mean, the obvious answer here is if we need to subtract initial lead or common lead, if we don't do that, our ages will be too old. Okay, so Pete talked on this. The idea here is that we have some sort of lead evolution models that describe how the crust has evolved. Now, we need to think, are these lead models appropriate across the planet, or are they more regionally specific? Now, fortunately, because the amount of common lead in zircon is low, we probably don't need to worry too much about using regionally specific lead models in zircon because we don't need to make much of this correction. But for other minerals, that may become more important. Okay, so very quickly, how does the 204 correction work? We start off by needing to make an assumption on the sample's age. That's not very palatable, but we actually have to do that because that then allows us to make a prediction about what ratio of 204 to the other radiogenic isotopes of lead is present to allow us to do our subtraction. So this actually works out remarkably well for zircon. But what do we do when 204 is much larger? What do we do when our lead isotopic system, in terms of our ratio of 204 to those other lead isotopes, is a little bit different from regional models? And we can prove that's the case in many situations, especially for environments that titanite and apatite might grow in. So we need to use a different technique. And when we're actually downstairs measuring our 204, it's actually a big issue. It's a small isotope, it's a low amount of it, so it's actually quite challenging to accurately measure. But even more problematic is that our gas that we use, especially on our mass spectrometers downstairs on our laser ablation system, so the gas that we use in our laser ablation contains mercury, which overlaps on the 204 peak. So we need to carry out a subtraction. We need to measure 202 mercury and do a subtraction then from take away 204 mercury to get an accurate 204 lead measurement ratio. And that all brings uncertainty, and it makes it actually quite a challenging approach when we are doing laser work. So how do we get around that? Well, we go back to Pete's nice diagram. He talked about this, the Terra-Weisselberg plot, and this helps us because if we have a simple mixing system between a radiogenic component and a common component, it will lie on a simple mixing line here, where the upper intercept on the ordinate axis gives us information about the common lead composition. Analyses with higher uranium would produce more radiogenic lead, and they will plot lower down on this diagram. So you can see here on this Terra-Weisselberg diagram, color-coded for uranium content. Those analyses with higher uranium are plotting lower down on the diagram. They've got a larger radiogenic component. Those analyses that are lower in uranium are plotting further up on this diagram and have more common lead. The challenge kind of comes when we see arrays that fan at this end, telling us perhaps that our crystal has grown or regrown in communication with different lead isotopic reservoirs. But we can also see data migrate to the right, either telling us that there has been new growth of a radiogenic component or there's been some lead loss. And we'll look at examples of where the mixing lines are a bit more complex and what techniques we can use to try and deconvolve those situations. So when I think about geochronology and isotope geology, I think of it kind of as a scale from techniques and isotope systems and minerals at one end that are geochronometers, and at the other end, isotope tracers. And we're going to have talks later in the day that kind of cover this isotope tracer end. But at this end, we're looking at clocks. And we tend to use specific diagrams for that in the uranium lead system. For other schemes, there may be some source information trapped within these as well as being a clock. So they might not be brilliant clocks, but they might give us source information as well. Whereas right down at this end, things like apatite, they don't have any radioactive decay within them. They trap the initial ratio of the system. So they're a good indication of the source. And we tend to plot this information on weighted mean diagrams. Okay, so what we're basically going to stick at in this talk is look at apatite uranium lead and titanite uranium lead. So they're right down the end of being a good chronometer, and less information about source, where the fluids that maybe produce these crystals grew from. So if we wanted that information, we might add on strontium isotopic signatures onto our uranium lead age information. So another scale I like to think about is the scale between a geochronometer and a thermochronometer, where this system, the daughter product is escaping until a specific point in time where this is the idea of blocking temperature. So at this end, we're looking at systems such as zircon, uranium, lead that close at a high temperature, so they accumulate all of their daughter product. Whereas isotopic systems and minerals further down this end of the diagram close at lower temperatures. And this is really important for us because it provides a mechanism to track a parcel of rock through various time temperature points. So you can see the kind of common uranium lead minerals up here, monazite and zircon, whereas other minerals and isotope systems such as argon in amphiboles or rubidium strontium in micas, we're giving us more mid-temperature processes. And then right down at the far end, we're getting, systems like uranium, thorium, helium, and apatite, fission track, and that's stuff that Martin's going to talk about. All right, so let's start off with titanite, and I wanted to do this more by way of a case study and show how titanite could be used to resolve some geological processes in Greenland, but also demonstrate some of the concepts that we've been talking about. Okay, so titanite, why is it good? Why do I like it? Well, I like it because its crystallization temperature is quite broad, and it can tell us about a wide range of different processes. It also tends to form in a wider compositional range than probably zircon, so we can find it in some more mafic rocks that don't have zircon. So it becomes a useful tool because it opens up the compositional array of material that's suitable for geochronology. Titanite tends to have relatively simple growth relationships. Now you could argue that's a good thing, but you could also argue it's a bad thing. Zircon is great because we can, we've got this mass archive of crustal evolution of the planet, and that's helpful because we've got, cores of grains that can be much older. But that kind of complicates things. It makes imaging really important for doing zircon geochronology, whereas with titanite, they don't seem to really be as prone to inheritance. They can have inheritance, but nowhere near as frequently as zircon. They also tend to recrystallize in entirety, so we don't seem to see as much lead loss effects. So that's good because it kind of makes the system a little bit simpler, and it kind of helps because it means that we more commonly see simple, common radiogenic mixing lines rather than more complex arrays of data that reflect these other processes as well. Titanite also has got quite well understood chemical reactions, and they fit quite nicely into work on pressure temperature space, so that's helpful. But this is the big problem. Titanites can have quite low uranium, and that creates challenges because it means the amount of radiogenic lead produced is quite small, and the ratio between the radiogenic and the common lead cargo can be quite high. So we have to have a mechanism of addressing that. So prolific gets a smile. Simple growth relationships gets a smile. Tends to be understood, and we can fit it into Tim's PT work. That gets a smile as well. But that's one of the challenges that we need to address, and that's what I'm going to touch on. So what we're going to do is we're going to go off to Western Greenland. We're going to go up above Disco Bay, and we're going to look at the Karak group. And we're going to look at some samples from really nice exposures of a sequence of basalts and also tuffs. The reason this sequence of rocks is interesting is they contain massive sulfides, which are potentially important for some mineralization in Greenland. So we look at our sample data that we're plotting on these Terra-Wasserberg diagrams, and we've just stacked them up. And we see our lower intercepts clustering down here at the radiogenic end are quite nice, and they're all around 1770 MA. So that's great. Okay, so it looks like a simple interpretation of that would be that the lead isotope system in our titanite closed to diffusion of lead at that time. The upper intercept is also kind of interesting, and it's quite consistent. So we look at the upper intercept there. The upper intercept is consistently around 0.8. Now, the reason that's kind of interesting is that if we have our normal lead models, this is a Stacy Kramer lead model, which I guess Jana will probably talk about some of the different lead models. But this lead model predicts that for titanite of 1770 MA age, we would expect to be getting a 7:6 ratio of around 1. Those intercepts don't really go around 1. They tend to be around 0.8. Around 0.8 is kind of consistent with modern day lead on average in terms of its 7:6 ratio. So that kind of brings up the question, are we simply seeing a mixing line between radiogenic lead and modern common lead? Have these crystals somehow be able to exchange lead with the local environment? Or is 0.8 some sort of mixed signal of ancient and some radiogenic lead from the precursor mineral that our titanite grew from? And that's quite an important question to address because it has a bearing on how we think titanite has grown, but it also has a bearing on how you might perform common lead corrections on titanite. Is it okay to use a regional lead model, predict a common lead value, and use that to project through your data to calculate an age? Or do we need to consider other processes there? So basically, that's what I'm summarizing here. Have we incorporated lead during later events? Is that why we're getting this 0.8, or is the common lead trapped during growth of the crystal itself? We can use chemistry to help understand this. We see some high lead concentration grains also have a high common lead cargo, but we also see a kind of the relationship we expect. We would expect to see higher uranium grains with more radiogenically produced lead. So there is that kind of relationship there, but there's something else going on in terms of the chemistry. In terms of the mineral, the petrology, the titanite grains are sitting within a amphibole and plagioclase matrix, but there is also micas that tend to surround the titanites. The titanite postates primary clinopyroxene, and there are some other phases within the rock that are that contain uranium. Okay, so how do we address this in a little bit more detail? One of the things that we can do is we can look at the microstructures, and one of the things you might ask yourself is, has common lead been able to migrate into the crystal through deformation features within the grain itself? So we have two grains. We've got a grain that is from the main radiogenic cluster, and then we've got a grain from the higher common lead component. You can see their trace element chemistry is a little bit different. So grain A has a structure within it. Grain B, which is the higher common lead grain, is relatively undeformed. So what we're going to do is use some atom probe work to try and understand that mechanism of common lead ingress, or is common lead intrinsic to the grain itself. The way atom probe works is we take a very small sample, use ion milling to fine it down to a needle. That needle is then heated up using a pulsed laser beam. That pulsed laser beam releases atoms from the surface of this needle. It goes through a focusing system and it arrives on a position-sensitive detector. So isotope of different mass will arrive with different speed. So they'll have a different time of flight. So they will arrive on the position-sensitive detector at different points in time. That allows us to reconstruct in 3 dimensions the needle itself. So we can get an isotope map of this needle. reconstructed using this atom probe and the time of flight mass spectrometry. So although the mass resolution isn't great and it's difficult to use this as a dating tool, it's very useful for understanding on the extremely small scale the compositional and isotopic makeup of a sample. So our first needle, which is our low common lead grain, we have a reconstructed needle, and I bring your attention to the fact that lead is homogeneous, but there is some structure here where we see enrichment in aluminium, iron, potassium, and magnesium. If we flip this needle around, we see this kind of banded effect. So this needle was collected from very close to a low angle boundary in the crystal. So interestingly, what this is kind of suggesting is lead isn't able to move, but other elements are able to move through structures within our titanite. This is just a reconstruction across the dislocation. So we can see, importantly, lead is homogeneous, shows no difference, but these other elements show either enrichments or, in the case of titanium and calcium, slight depletions. So what's actually going on? And this is, I think, really interesting. This is a boundary in a grain of titanite, and it's being indented. This indentation is causing screw dislocations in the lattice where the lattice is opening up. And those dislocations are migrating towards the boundary. And that's how we actually pass elements through a deformed crystal. So most people would think they migrate straight along the boundary. They don't. They migrate into the boundary through these kind of screw dislocations. But what this data is saying is that lead is too big to fit into these screw dislocations, whereas other elements can fit. We go to the high common lead grain, and everything appears pretty homogeneously distributed. So you can see where this is heading. It's basically going to say that, unsurprisingly, that lead is an intrinsic signature trapped in the grain during growth. So the common lead component is the common lead component at growth. It is not a later effect, which means that 0.8 is a signature of the local growth environment of that titanite when it grew or recrystallized. So how can we get something that's more radiogenic than our predicted Stacey and Kramer's regional lead model? That lead model actually seems to work quite well for Greenland based on work on lead ores. But in the local environment of our titanite, what's likely happening is we're simply breaking down an older radiogenic mineral. So if we had an older uranium-bearing phase, we break that down, we mix that with our regional lead model, we're going to be on some kind of mixing curve between the two, and that's easily going to allow us to reduce the lead isotopic signature back to what we see. So we can play those sort of games to create a kind of a petrogenetic model that we think works to explain the chemistry and the growth history of our titanite grains. So we suggest uranium-bearing phase breaks down, undergoes recrystallization. It releases its lead cargo. That lead cargo then gets reincorporated into titanite. When the titanite is growing, the titanite grows in competition with another phase. That other phase sequesters some of the rare earths, but it doesn't affect the uranium cargo in our titanite. Our clock essentially is started at this time in our titanite grain, and we have a later process which seems to be associated with epidote and also micas that fractures some of our titanite grains parallel to the fabric, and that also migrates in aluminium, iron, potassium, and magnesium, but isn't able to migrate in lead. So the combination of petrology with some of the imaging techniques, I think is useful in reconstructing the growth history of our mineral grains. So they're not only simply tools to tell us about the timing of a process, they're kind of chemical capsules that tell us about chemical processes happening in a rock during its petrogenesis. How much time do I have? Plenty of time. Good. Yeah. Up there. Yeah. Oh no, not very much. Right. I can do appetite in like 2 seconds then.
What do you reckon the precursor?
That's a very good question. So I think we hazard a guess that it was perovskite, because there is inclusions of perovskite. So, yeah. Okay, so what do I have? 5 minutes-ish? Yeah, okay.
Spent too much time on the happy, sad clocks, mate.
I did, right. Okay, so appetite is another very useful tool. Pete's probably going to cover this in more detail later, are you? With strontium and appetite. Okay, so we have zirconium plotted against full rock silica, and so our zirconium, kind of peaks out around 65. So our zircon record is going to be biased to probably the more felsic end. That can have issues for how we reconstruct, crustal processes and crustal evolution through time, because our record, if we're looking only at zircon, could be more biased to those periods where we're only getting more felsic rocks. It means that apatite becomes useful. Apatite becomes useful because it tends to grow in a less silica saturated melts, and opens up our kind of compositional range for geochronology down to lower silica concentrations. Again, we're going to go to a similar area in Greenland, on the west coast of Greenland. We're going to go to the Achaea terrain. And the reason this area is interesting is it's been proposed as good evidence of, or to retain evidence of, early Earth horizontal processes. So in other words, subduction style processes on the early Earth. And, you would contrast that with the Pilbara Craton, for example, where everything is in a much more vertical sense, with sagduction style process where we're dropping greenstones, melting those, and creating granite domes. So a key kind of question is, does this area preserve evidence of horizontal tectonics, and could those horizontal tectonics reflect a Proterozoic overprint? How do we diagnose a Proterozoic overprint? All the zircon record seems to be recording Archean processes. This is where a lower temperature chronometer potentially comes in, like apatite, because it might tell us about these later overprinting processes. Some of the apatite data just plotted up, and you can see we're beginning to see complexities in these data sets. So you can see these sort of submixing lines between the radiogenic and common component, but you can also see data scattering away from that line. That potentially is suggesting we're seeing differences in closure temperature between different grain sizes, or are we seeing a recrystallization process in some grains? No matter what, it's telling us about a later process happening to that apatite. If we plot that data up in a histogram, you can see all our zircon is bolted on at about 3 GA, but our lead system is in the apatite is telling us about an event at about 17 to 1800 MA. And that's potentially quite important, because if we look at the where the Achaea terrain sits, it sits very close to Nastikidian origin, but the effects of the Nastikidian haven't previously been inferred to have stretched this far south into this terrain. The question then becomes, does this apatite data reflect something, a time temperature point? Does it reflect a closure age? Or does it reflect a recrystallization process? If it was simple lead diffusion in our apatite crystals, we might be able to look at the diffusion pattern and make a prediction about a time temperature pathway. But if it's a secondary growth or recrystallization process, that's actually quite challenging, because what it's then telling us is discrete time markers for different processes. So it's important to be able to distinguish between a lead diffusion process and a secondary growth or recrystallization process. And that is what we can use some of the apatite chemistry to help us distinguish between. Traditionally, all apatite has been thought of as a mineral reflecting volume diffusion that you can use to tell you about the lead isotope blocking temperature time point. But we should be aware of these processes. So I'm only going to do one sample here to show you how we can distinguish between a recrystallization process and a lead blocking process. So nice TTG with banded gneiss. We've got a tonalytic component at 3GA. We've got a slightly older diorite component, but we also the rock is shot through with 2.8 granite. We're going to look at apatite very quickly from the tonalytic component. Okay, so here's the apatite from the tonalytic component. We can see already texturally it's quite complicated, and it shows what looks like some recrystallization textures. The lead isotope data scatter. They don't simply form a single mixing line. And chemically, the apatite is also different. The rims of the apatite have a lower, actually I'll do it with this because it's easier to point out. The rims of the apatite have lower magnesium, but they also have a lower light rare earth slope. Whereas the older apatite, or apparently older apatite, with the forming this older mixing array, seems to have higher magnesium concentrations, but also a flatter light rare earth. A steeper, flatter rare earth slope. So the point of this is that there's been some chemical modification and recrystallization of our apatite grains, and we can say something about the pressure temperature conditions that occurs under, because there's relationship to epidote in this recrystallized domains. So we can say something about the time temperature conditions of that recrystallization process. That occurred probably at around 500 degrees C, and that's also taken to be the typical lead blocking temperature of apatite. So we need to be very careful, in kind of summary, that when we're using apatite, we don't simply use the age to infer a process of lead blocking, because it can also be related to recrystallization. I'll probably leave it at that.